Find the volume and surface area of the solid obtained by rotating the region bounded by y equals 1 over x for x is bigger than or equal to 1. Rotated about the x-axis. So the function y equals 1 over x. But what we're doing is allowing x to get as large as possible. We're going to let this go off to infinity. And we're going to spin this about the x-axis. So what will happen is we get this horn type shape. But this goes on forever. We're going to find the volume, and then later we'll find the surface area, and we'll find something very surprising. Volume first. So we take this function and we rotate about the x-axis, and definitely going to go with a disk method here. Draw a rectangle perpendicular to the axis of rotation, and so that would be disk, and the formula for volume with disk is pi times the integral from a to b of the radius squared. The radius is basically the height of the disk, which is going to correspond to the height of the function. And so we just integrate that from a low limit of 1 all the way to infinity. This goes on forever. So we have the volume to be pi times the integral from 1 to infinity of 1 over x quantity squared. Well, that's just 1 over x squared. And to integrate that, we have to think about it as x to the negative 2. So that we can use the power rule in reverse on that to find the antiderivative as x to the negative 1 over negative 1. Better written as negative 1 over x. Okay. It was improper, so we needed a limit, and the variable t is going to approach infinity. That replaces the upper limit there, and now we have an upper limit of t, a lower limit of 1. We plug those in, and we allow t to go off to infinity. Well, what happens? We have negative 1 over a very large number. That's a very small number. It's going to go to 0. And then we have this double negative here canceling to give us a positive. So final result then would be the pi from the formula for volume. And we conclude then that it's a finite volume. Now let's take a look at the surface area. Surface area generally is a little more complicated calculation because of the setup for it, the integral, and actually sometimes you might not even be able to find the integral in a closed form. So what we're going to go to set it up, and to do it we have to figure out which form we're going to use. Since we're rotated about the x-axis, we know it has to generically look like 2 pi times the integral of y ds. The y here is the radius, and ds is a piece of arc length, infinitesimally small piece of arc length. And so we have options then. If we want to do this in x, then this y can't exist. We have to replace it with f of x, and then the ds has to be in x format. If we're going to do it in y, though, there's no reason to change the y. We leave it as a y, and then the ds needs to be in y format. We're given a function y equals f of x, and we're given an x range, so that's going to lead us to think that we should go with this x version here, where we replace y by f of x, and we have the x version of ds. And we're going from 1 to infinity. All right, great. So if our function is f of x, now we need to take this ds part and simplify it. If our function is f of x, 1 over x, then the derivative of that is negative 1 over x squared. You know, think about it as x to the negative 1 and use the power rule on it. Negative 1x to the negative 2. Then that's negative 1 over x squared when simplified. All right, great. So that's our ds then. We have to then square that. If you take negative 1 over x squared and square it, you'll get 1 over x to the 4th. And typically we would go further with this. Let's leave it like this though, and then plug it in and make an attempt to integrate it. We're going to find out that we're going to have trouble with this integration though. Replace the y that was in the formula with our actual f of x function, 1 over x, and now replace the ds with this simplified version that we have here. And this is a difficult integral to actually calculate. We'd have to do a u substitution, maybe a trig substitution after that. And so instead what we're going to do though is show that it's divergent. Okay, so we're going to use the direct comparison theorem, which says if you can find something that's smaller than this integral, a function that's smaller than this function that you're integrating, and the area on it is infinite, then your area must also be infinite. Let's take a look at that. If we allow x to get very large, right, as x goes to infinity, then we have this 1 over x to the 4th term. Well, that's going to go to 0 as x goes to infinity. And so then we just are looking at the square root of 1. And so that's just a 1. And so 1 over x would be something that we can compare it to. We can always be sure, though, that ours is larger than that because of this adding on some positive amount. This is an integral that we can go find, and we'll see that it is infinite. And this is our surface area integral. So we allow t to go off to infinity. We find the antiderivative, and we plug the t in, and we plug the 1 in. Well, natural log of 1 is just 0. But as t gets big, natural log gets big, although it grows very slowly. And so what happens is that we get that this will approach infinity as t approaches infinity. So our surface area is larger than this. Well, so it's also infinite. So wait, the volume was finite, but the surface area was infinite. Something is not right about that. Let's take a look at it. So another way to think about the volume being finite, it is this horn shape, remember? And so we can fill it with some finite amount, pi cubic units of paint. If we were trying to get an idea of what it means for the surface area to be infinite, though, if we were actually trying to paint the surface, we couldn't do it. It takes an infinite number of square units of paint to cover its surface. So we can fill it with a finite amount, but when we try to paint it, it takes an infinite amount. That seems strange, and it's actually so strange that it's given its own name. It's called the paradox of Gabriels Horn, or more precisely, Torricelli's trumpet. Evangelista Torricelli discovered this without calculus. He was born before the age of calculus. In 1641, he discovered this paradox, and people thought he was a lunatic. But it turns out that it actually can be resolved. And it's the idea of our physical notion of paint that holds us back. You see, real paint will have a finite thickness. And so, let's say it's the thickness of a paint molecule. At some point, this horn becomes thinner than the thickness of a paint molecule. So we won't be able to, actually fill it with the real paint. And of course we wouldn't be able to paint it either. And so what happens here is that this notion of actual paint would be more for some paint that has some infinitely small thickness, which isn't actually possible. But if there was such a thing, then we could fill it with a finite amount and we can actually paint it. Although it's infinitely thin, we can paint over this infinite surface. And there's a nice source there if you want to check it out. A nice blog on that. So anyway, it's called Gabriels Horn, and it's a paradox where we have a finite volume of pi, but an infinite surface area. Great.